All right, welcome to class 17, and these are bolts. We're going to be covering the bolt nomenclature, and we're going to talk about power screws. So there's those two topics today. So it's sort of like bolts 101 and power screws. And I think I am going to do the lecture in this video and do the examples in another video right here. Okay, so ready for bolts 101. Okay, so we got screws, fasteners, and the design of non-permanent joints is what chapter 8 is considered. And you're hearing a 3D printer in the background. It's a lovely sound, isn't it? I should get one of those quiet cards that can make it quiet somehow magically. I don't know how that works. So the types of topics that we deal with are power screws, by which we mean transmitting rotational power, torque and motion, into linear power. That's force and motion, right? So we have torque into translation, right? Rotational into linear motion. And here's like some power screw types of things. You could have like a jack kind of thing that's turning the nut right in here, and it's going to lift this up. You might have seen the power if you've ever taken a closer look at the lathes and the automatic feed, right? Where it's feeding the trying to remember the name. The carriage, right? It's moving the carriage along right there. That's like a power screw. Or like I mentioned, a jack. Or here's a really simple example. We could have a C-clamp. And so we're turning the thing, and it's turning, and it could be crushing or holding something in place. We could also have a bolted joint stiffness with preload. That's an awkward way of saying you want to bolt two things together, and you want to make sure that they don't come unbolted. So you put some torque onto this, and you crush this joint right here. And that's what's going to be covered in the next class. So this is in pressure vessels when you're trying to put a lid on something so it doesn't leak, or joint some pipes together and make sure they don't leak. You need to have a preloaded joint. And then we can also have bolts that are clamped joints, right? So that's where we're going to clamp some joints together, and we're going to try to resist some force, not necessarily in line with the bolts, but kind of like perpendicular to the bolts. And it's kind of the same deal with rivets, right? So you can think of a riveted joint as they're showing right here, and you're trying to pull them apart. You could also have them cantilevered off to the side. So that's going to be the classes, I believe. Let's see, today's class is 17. So class 18 is preloaded joints. I think class 19 is the shear joints like this. And then class 20, is that next? Yeah, is going to be like these cantilevered types of joints. So there's all different types of things where in these non-permanent joints. So we want to go through and talk about the nomenclature. So I will flip my screen around right here. And then we're going to flip back here in a minute because I have instead of passing around the bolts. Okay, come on, flip. There you go. All right, so some of the nomenclature that we deal with a pitch, right? And so like the pitch is going to be, which we often will call just a P. All right, so it's not the same thing as with gears, although it's got sort of underlying kind of the same ideas. The pitch is really the distance between adjacent threads. This would be much easier if I would just write this thing out again. So we might take a look at this and go, this is, boom, the pitch. P. And so if you take a look at the beginning of one thread and then you go to the same spot in the next thread, that distance right there. And the pitch diameter is this theoretical diameter. We don't really have anything on here that is the pitch diameter. So it's sort of like, it's kind of the average diameter, but it isn't quite the average diameter. So this is like the pitch diameter. Then we have the major diameter. Okay, so that is a real one. And that's usually, but not always, the shank. But generally speaking, it's going to be what the stock that the thing was made out of, right? So there originally was this stock cylindrical rod, and that's going to be the outside and the largest diameter. And then we have the minor diameter, which is also known as the root diameter. That's supposed to say diameter. Okay. And so this one right here is the minor. And the lead, now this is a little weird. This is quite often, it's almost always the same thing as the pitch, but it could be different. So I have a couple of examples that I tried to put together for you so that you could see here. So the lead, which I believe they like to call lowercase l, is the distance a nut moves with one turn. And that almost is always the same thing as the pitch, but it can be something different. And you go, well, how is that possible? Well, we'll see in a second. You can't, well, the thing is, you could have double and you could have triple. I guess you could have quadruple threads, and we'll explain what that is, right? And then we also have UNC. Okay, so this is the United States of America, and we have the Unified National Course. And I forget whether it's, yeah, it should be, that's that spelling, of course, right? And then you have UNF, which is Unified National Fine. But you also have extra fine and so forth. But these are the two big guys, UNC and UNF. And we'll see this right here. So what we have over to the side, what you're seeing is the this right here is the maybe the geometry, or it's really kind of a rough geometry of what a typical UNC would be. So you can see with the proportions. But there's actually some like rounding off of this type of thing, and we'll talk on more later. But most threads aren't cut, but instead they're kind of forged, right? So your typical for production threaded piece isn't cut, but instead I'm trying to think of the correct words. It's like hot forged in here, where we actually rolled. That's what we say. We actually roll instead of cutting most threads, and we'll see why that is. And the act of rolling actually puts little fillets down on everywhere and rounds the thing off. But let's go back and let's mention these guys right here, that Unified National Course and Unified National Fine. There's some history to how this was came about back when, it was all really related to automobiles, because that's where like one of the big production started to take place. And there was a time where everybody kind of made up their own mind of what pitch to use with which diameter of bolt. And so one of the consequences is that like you kind of had to go to whoever built the thing to replace even a simple bolt. And that wasn't a very efficient and wasn't a very good way to do, although the people who built stuff really kind of liked that. So instead, we got together and decided these are going to be the standards that we're going to use. And so there's probably a big conference. And this is one of the, probably the birth of some of the first standards, right? Where we talked about pressure vessels being some of the first codes were created because of boiler explosions and the birth of the ASME. Well, some of the first standards were created, and so bolts, like having something that was like the standard size, standard designations of pitches with a particular diameter. That was some of the first standards. So let me explain what lead is right here. Okay. Well, yeah, do I want to do that? Sure. And to do that, I'm going to flip my screen again. Okay, so butt it up. Let's keep all that. Oh, I got another 15 minutes until class. I probably don't have enough time to finish this video. So anyway, right up here is out of the book is example 8.1. Right, so these are the dimensions that get used in example 8.1. And if you were just to take a look at the cross section of this, you might not be able to tell, but this is actually a double-threaded bolt. And the way that you would be able to tell here is, let's roll this thing back till we get down there. Okay, and then we do this swept cut. And we take a look and we see what is the sketch that was used to make this cut. And you'll see that they're actually two rectangles, right? So look at the top of this. You can see there's two places where it starts. And so these are running in parallel with each other. So now for every rotation, this thing is going to move twice the pitch. So the pitch is really just the distance in between the threads, right? From like maybe this edge right here I'm pointing at to this edge, right? You want to not just talk about the gap, but also the gap and the thread, right? So that's the pitch. The lead is actually the full distance is going to be 2 times the pitch in this double threaded piece. And what I like to think of it in terms of perhaps if you were to take 2 wires, right, and let's see if I can get this up in here. All right, so I put a tape around it, so it's kind of hard to see. In fact, this is actually 3 wires. So this would have a triple threaded right here, so where you could see that just follow like the black wire, that would be a single, and then the green and the red. This is how they would be arranged. One very common double threaded thing that you would see. In fact, I think this is actually a triple threaded. Let's see, I don't think you could really show on the water bottle, but you will see that if you take a look at your water bottle, there's actually 3 beginnings of the thread, right? So you can take a look, there's 3 separate spots. So this is actually a triple threaded piece. And what that does is you don't have to turn it as much to make the amount of axial motion that's going on right here. I think that also the same thing is true with lots of different tops, like on toothpaste. So check that out. It's kind of an interesting thing. So we can go and close this up. If we want to describe the bolt to somebody, we need to give certain words, certain names, certain specifications. And so right here is the American, right here. And by the way, I don't know where this is in the book. I don't think it is in the book, but they do ask problems like this somewhere like in the very beginning of the chapter. So what you're walking through here is we have the nominal diameter, and then we have the threads per inch. That's usually really the important 2 things. And then you'll also often see that UNC or UNF right in here. I don't often always see the length put down there, but if you wanted to follow the specifications, you would. And they include the inch right in there to tell you that it's an inch. And then we also have the class of the fit, and I need to look that back up again. But I think that's like really the precision of the bolt. And once again, I don't usually see that written up right here. Then you have the grade. This is really the material and really the strength. This is where you know how strong. And we can look this up in a table. We have an abbreviated table in our textbook. And then we have the head type, right? So this goes for the entire bolt specification. Metric, they usually have this M right in here. They have the nominal diameter, 12, and then they put the pitch, right? And so this is going to be, I believe it's going to be the millimeters per thread. And as opposed to the threads per inch, I think this is the millimeters per thread. But don't hold me to that. But we need to check on that. It's easily to check. We just go to the book and take a look at the tables in there. And they got ISO, International Standards Organization. and then now have the material class, right? And then we have the bolt head type. I believe that class is going to give us the same thing as the material grade, right? And that grade is designated, by the way, in bolts. There's going to be a pattern on the top of the bolt head. I think I'm jumping things here, but there'll be pattern on the top of the bolt head, or something will be written on the top of the bolt head, not a bulkhead. So I go back to my camera and take a look right here. And so here is a very common bolt. Let's see, right in there. And you'll see that it's got these three lines right here. That's the designation. There's also like probably a manufacturer's mark, and so these could be quite different. I did want to look at some of the other features of the bolt while I have it right here. So you've probably seen many bolts before, but maybe you haven't looked that closely. You could try to see some of the features where there's actually a little piece right up above where things are actually supposed to rest, right? So it's actually supposed to be landing on right here. And there's also kind of a fillet already made into it. And then as you go down, you can see on the shank right here, it starts to get smaller right there. All right, so this one actually, I think this one, yeah, no, it's probably true. It did get made out of this, but these are rolled threads, right? So they're not exactly cut. It's been rolled into this. This was like, red hot, not melting, but enough that they could forge the thing in there. And so places where a bolt will break, and I talk about this later, can be right here, and then right here. Right, so those are the three main places that bolts end up breaking, and we'll look at that in some more. So let's see, I got another 10 minutes before I got to go back to class here. And here is an excerpt from Table 8.2, and so this is the United States UNC. They have both UNC and UNF, and just as examples that you could have a 1/2 inch bolt. Right here is this nominal major diameter. It's going to be 13 threads per inch is standard. It has a tensile stress area. Okay, so this is not a real area, right? This is just, we use an AT, but that's the one we use for stress. Right, so the only place that you can really get it is from this table. I think in the subscript or the bottom part of this table, they might have a formula or approximate formula that you can use to try to get this tensile area. And then we also have the minor area. That's the actual one that's at the bottom, right? So it's kind of interesting that you don't actually use the smallest diameter here for the stresses. You actually use this tensile area that we get out of off of this table right here. And then you can see for UNF, all right, so the fine series, you can see for the same bolt, we have more threads. We have 20 threads per inch instead of 13. And what the fine threads are often used for things that are going to be like high vibration are taking place, and so that's going to help prevent them from loosening up because of that vibration. And it also usually will be used in more precision types of pieces of equipment, like on a race car and that type of thing. Quite often, fine threads, those won't be reusable bolts. Quite often, they're going to be for like they would toss them away and use a fresh set once they've been used, tightened up, and then loosened and taken apart again. They'll toss them away. But you could see that they have a slightly bigger amount of tensile area, but that's not really necessarily the reason why that they get used. It's mostly that we have that more threads per inch. So we're going to talk about the mechanics of power screws and examples of power screws right here. So here's the two. We have square threads and Acme threads. So here's the geometry of square threads and Acme threads. Over in here, these were let's just say that these are standard bolt threads, right? The kind that we in the bolt that you've seen. But like often in power screws, we will have these literally square threads and Acme threads. And once again, I have a picture where I can use my camera here to show an example. Okay, so I believe this right here, let's see if I can should get like a flashlight, so you can see that the threads are square compared to and I believe these are Acme threads. There's like a taper, not a taper, but there's an angle to them. Instead of being perfectly perpendicular, there's an angle here and an angle here on top of these for the Acme. So holding them side by side, you could kind of see that there's a difference between them. Here's actually a weird one. I don't know what that one is. You can see that it's actually well, it's kind of tough to see. Well, actually, now that I look at it in the light, it almost looks like it's yeah, I guess these are just pretty much regular threads. So yeah, you're comparing the three things to each other. We have Acme on the top, regular bolt threads on the bottom, and square threads at the bottom. I said on the bottom. We have regular threads in the middle, and we have square threads on the bottom. And sometimes it's a little tough to tell. This is off of a, I think that these are closer to square threads than anything else. And when I have people do an assignment with this, we try to figure out what's going to fail first. Is it going to be this bolt threads, and they're probably going to fail like right in here? Is it going to be from the bending of this, or is it going to be from maybe this little handle? Probably this little handle is going to bend, and you know. But if you were to just put a force like right on the end of this thing, and you were to torque something down, and like that was inside here, right? Which would go first onto the thing? And now this is made out of different material. This is cast iron right here quite often, and these made of some kind of stainless steel, chances are, and I don't know for sure, but this is only like $15 at Lowe's, so it's probably not going to be very strong. So that's really some of the nomenclature in this class, and I got 5 minutes until my other class starts. And see, there's a reminding. I got a little reminder that the class is going to start soon. So we're going to end this video here, and we'll just separate the things out together. And I will talk more about power screws, and talk about the stresses that are going to be inside them and the friction that you would get from them. So there we go. And the end. Boom.